Welcome to the shop. I'm continuing NQALHA Production Run 5 on my new Haas Mini Mill 2, and things are going really well. Little bit by little bit, I'm getting more comfortable, more confident, faster, more accurate, and I'm making a lot less mistakes. Kind of a side issue here, Bobcad, the toolpath software that I use, provides a scripting function in their post processor that is incredibly poorly documented with a whole lot of important information missing, and I kind of took it as a challenge and said, I'm going to figure this out. And after a lot of Google searching and a lot of scratching my head and a lot of mystery and a lot of confusion and a lot of what the fuck, why didn't they just write this down, I figured it out. So I can now do scripting in the Bobcad post processor. And last night, while I was thinking about the project, I realized, hey, you know, I can actually, probably, I haven't done it yet, I can do the tool management where I'm overcoming the limitation of the 20 tool changer on the Haas by kind of adjusting and matching position in the tool changer versus tool offset in the tool offset table. When I first solved the problem, I did it with a piece of custom code written in C++ that was a post processor that I run after the post processor. And I just realized that now that I know scripting, I can probably handle this all by setting up multiple tool cribs, each tool crib representing a tool set or a load of the tool holder, and then using the scripting function in Bobcad, be able to do it all in one oink without having to have external programs. So little bit by little bit, I'm refining this thing. Today's part is the most difficult and challenging part in the entire project, that involves many operations and requires fairly high accuracy. This part is the controller housing, and in my latest design, in the 2.3 version design, I've changed the way the heat sinking works, where the circuit board has motor driver chips on it. The chips get hot, and I like to be able to get the heat out of the chip and use the body of the controller as a heat sink. And so I modified the design a little in version 2.3 to provide a surface that actually let me show it here, that this little surface right here, I put some heat sink compound on it, and when the circuit board goes over this, the top of the motor driver ICs touch the surface of that aluminum and the heatsink compound, and provide a better thermal path to get the heat out of the motor driver chip. The other thing that has to be done very accurately on this part, the lever that releases the magnets on the handle, it got a little axle, and when you push the lever, it moves a piece up that touches a tactile switch on the circuit board. This tactile switch has a range of motion of 10,000ths of an inch. That's its full travel. And so it kind of requires the mounting surface of the circuit board and the hole, which is drilled at a really weird angle coming in through the side, requires that hole to be accurately positioned relative to the mounting surface of the circuit board. And in the past on the Tormach, I haven't been able to hold that dimension as perfectly as I like, and I ended up having to hand fit pretty much every one of the levers with a piece of sandpaper and just, take off a 1/2 thousandth, screw it back in, see how it feels. Nope, not quite right, take it out. And it's a kind of a long and tedious process. And little bit by little bit, I've been trying to improve all of my precision so that I can either reduce or hopefully eliminate the hand fitting. So also in the past, I was kind of like trying to figure out, well, where should the reference surface be for this part? And I erroneously chose the top of the extrusion to be the reference surface in the old days on the Tormach. And yeah, that's fine if the extrusion is perfect. And of course it isn't. So I was actually relying on the mill tolerance of the extrusion for some of my precision. And when I realized that, I included now a skinning operation where with the part securely clamped in the vise, I skin the top, and then without removing it from the machine, do all the rest of the milling operations. And hopefully this will result in very much tighter tolerance. And of course, the mini mill holds tighter tolerances in general than the Tormach did, partly because it's just a better machine, and also because the Tormach tool changer, the TTS tool holding system, it really wasn't that rock solid, and sometimes tools got loaded in not quite the perfect position, resulting in the poorest accuracy on the Tormach was in the Z-axis. The X and Y were actually quite good, believe it or not. So this part is going to be fairly aggressively hogged out of 1-inch thick aluminum material, 1x2 aluminum material, and I'm using the Lakeshore Carbide 3-flute roughing cutter, the aluminum shredder, that produces very, very fine chips. And since I'm doing a deep pocket in a fairly thick piece of material, chip evacuation is really important. So I've already made one, so I'm not going to go through the process of figuring out how to do this tool path. And I'm also not going to show the probably 6 hours that I spent yesterday at the computer refining the tool path, simulating, refining, simulating. This is a very, very, very hard part to create tool path in BobCAD. I'm creating the tool path as a sequence of 2D layers as opposed to taking a solid model and trying to do it all in 3D. I actually did that. I actually have a solid model in SolidWorks, and I brought it into BobCAD to see if BobCAD was smart enough to figure out how to just mill it by selecting the solid model and saying go, and it didn't do a very good job. Of course, in SolidWorks, as I constructed the solid model, it was constructed as a series of 2D sketches, and the existing Tormach tool path that worked and produced acceptable parts was a series of 2D tool paths. And so after wasting far too much time trying to get the 3D tool path on the solid model to work properly, I went back to the 2D tool path, optimized it, made it much, much more aggressive now that I have the more powerful machine. And anyway, I'm going to stop talking and let's get to cutting. Let's make some chips. So here we go. Full speed rapids, full speed machining, skinning the top with my 3-inch 6 insert face mill that does just an absolutely beautiful job. Amazing cutter. So here comes the roughing operation, 10,000 RPM, 3/8 diameter aluminum shredder tool, operating at 200 inches per minute. there's a chance I can probably speed that up. I may be able to bump it up to 250 or 300, but no, I don't want to break the cutter. They're expensive cutters, and 200 inches per minute is giving me about 58% spindle load, and with the flood coolant and the small size of the chips produced by this cutter, I'm getting excellent chip evacuation. So who knows, I may go ahead and bump it up, but the performance is already so much better than the Tormach that I'm not sure how far I really have to go. And do I have to push everyone to a limit and break a cutter on every tool path that I design just to find out where the limits are? Or do I use the intuition that I'm starting to develop and say, yeah, maybe that's close enough? So I'm still debating this. The HSM toolpath is actually working quite well. I'm using a spiral ramp entry point that if you just plunge a cutter like this into the material, it builds up a rat nest of chips. And so by doing the spiral ramp entry, it doesn't build up a rat nest. It makes for very nice chip evacuation. So that completes the roughing cycle. I'm going to finish now using the 3/8 solid carbide from Lakeshore Carbide, running at 10,000 RPM, 90 inches per minute. In the old tool path, I, for some reason, decided that I needed tighter inside corners and used a 1/4 inch finishing cutter for the finish, and had to run it pretty slow because it's got a lot of stick out, and I was getting tool breakage if I tried running it too fast. Well, then I looked at it and really kind of like critically examined it and realized, I really don't need that tight inside radius. That extra few thousandths of inside radius doesn't really bother me at all. The slot that I'm cutting for the lever does need to be 1/4 inch, so I switched to the long 1/4 inch finish mill, also running at 10,000 RPM. Now I'm going to poke some holes using a full peck cycle because it's a small diameter drill and a fairly deep hole, and I don't want to get chips clogged. Now I'm going to just poke some holes, single pass. That's the hole the wires go through, 1/4 inch hole. And then the 3/16 hole for the mounting screws, also single depth, no peck. And then going to do some tapped holes, 632 tapped holes. The tap drill is a small diameter drill, and so I'm using the full peck cycle instead of the fast peck. I'm not sure I have to, but when drilling a 1/2 inch deep hole, and yes, I'm drilling a 1/2 inch deep hole, but only tapping it a 1/4 inch because, and even though I'm using a spiral flute tap that ejects the chips upward, I don't want to take any chances on breaking off a tap in that hole, so, drill the hole a little deeper and be a little careful. I'm running the rigid tapping at 250 RPM. I think I can bump this up. I'm not sure that I need to be tapping that slow. When I watch some of the Haas demo videos, it looks like they're tapping quite a bit faster. So I may investigate that a little and bump it up a little. Hope that spray doesn't get the camera. Okay, looking good. And the final 2 holes are 440 tapped holes, which was always a nervous kind of thing on the Tormach. I never broke a tap except once when I actually made a mistake and got the depth wrong and bottomed it out, but with the correct tool path. I never broke a tap on the Tormach, but was always a tiny little bit nervous tapping 440. We'll see how it goes on the Haas, but so far all appears to be well, and that's going to be the last hole here. And the part is complete. Looks to be a really nice part. The part looks to be very, very nicely made, and everything looks correct. So I'm gonna set up an indicator on my surface plate and inspect the parts just to see how close I'm coming to dimension. When I did the last run and inspected the last batch on the surface plate, when I made them on the Tormach, I was holding 5/1000ths, but you certainly know better than that. And it'll be interesting to see how my accuracy is improved now on the mini mill with the new tool path and the skin on the top. So that does it for this video segment. I'm going to turn the camera off, change a few things around, and I'll see you later. Okay, I've got the part on the surface plate, and I've got a dial indicator in place. And sure enough, the target dimension was 223, and it's measuring 222. So that's within 1/1000th on one part. So I'm gonna run the batch and then measure all of them and see what the repeatability is. But starting off within 1/1000th, hey, that sounds good to me. Most of the first operations were completed until I ran out of material. I'm just not doing very good at my inventory management, but I knew I was going to have to make another run to the metal supplier since my laser cut parts aren't done, so it's really no big deal. So I finished a bunch of them in the first operation and then made 2 new tooling plates. Now in the past, I used thinner material. I basically used whatever junk I had laying around the shop that I didn't want to use for real parts. I had some old 50-52 aluminum, and I would just use any old piece of junk that I didn't want to use for other things. And after making many, many parts, I noticed that, wow, I'm stripping out my screw threads. And so I've got 2 strategies that I'm working on here. The first one is just make the tooling plates out of thicker material and use longer screws. And the longer screws, more threads, will give it a little better of a chance to last longer. And then if that doesn't work, I'll drill them out and put in steel helicoils. So I made 2 new 1/2-inch tooling plates for the outside perimeter of the controller housings. And on the Tormach, I had to be, like with everything, I had to be really gentle and do it, slow feed, avoid chatter, and do it in multiple steps. And of course, on this machine, 10,000 RPM, do the whole thing in one step, get it done quick. And the cycle time on this is so fast that it's just amazing compared to what it used to be on the Tormach. So I'm going to go over, I've already made a couple of parts, so there's going to be no excitement on watching the development process. Although this Just in general, the development process is going a lot smoother. Mostly the stuff works first time. I have very little problems as I'm developing techniques. Here's my new tooling plates. I turned a little alignment pin here to precisely match the hole on the side of the part, and that gives me a pretty good distance here, so that, I mean, this little pin is turned within 1/1000th, and the screw is as good as it is, so it ends up giving me fairly good resistance to twist. So put the pieces in place. Then I needed to actually cut off some washers to clear the internal parts of this thing. Actually, putting it on the tooling plate takes longer than doing the machining operation. This machine is so fast that sometimes in the old world of the Tormach, I would have a part running and it would run really slow, and then while it was running, I'd cut a blank, deburr a blank, take the part that I had just made, deburr that, stack them, organize them, look at the setup sheets, write down some information, and I basically had a leisurely time doing it. Now, when I'm, the machine is running faster and I'm optimizing my tool path, and so now the machine is faster than I am. And in some cases, I'm just running around like crazy. Cut a blank as fast as I can, deburr it as fast as I can, deburr the part that just came off the machine. Oh no, the machine's ready. Can't let it sit there idle. So, wow, production has really increased, and now I'm the slow part. So, got the parts in place. Going to be using once again, using my new best friend, the Bobcat array function, to do 2 of them at one time, work offset 1, work offset 3. And so, here we go. Lakeshore Carbide, 3-flute, 1/2-inch cutter, 10,000 RPM. Boy, I love that 10,000 RPM. I'm so glad that I got that option on the machine. The standard machine is only 6,000, and I'm really glad I got the 10. So, doing the roughing around the corner, 60 inches per minute, and then the finish at 90 inches per minute. And yes, I could go a lot faster, but the surface finish that I get at 90 looks pretty good. So, boy, that is a fast cycle time. Now here's something that, notice that the parts are full of coolant. So if I just open the door and squirt it with the air, I'm going to get coolant all over myself. So I open the door just enough to get the nozzle in. And blow them off. I think when I was making the videos on the Tormach, I talked about how I didn't like a full enclosure, and I really preferred my kind of half-height splash shield. Well, I did and I didn't. When the splash shield worked, I liked having the extra visibility, but when it didn't work, I got soaked with coolant. And so I think I'm getting to like the full enclosure. It's really nice to be able to keep the floor clean, keep the coolant off me, and it's just better overall. So I'm going to go ahead and run the batch on the second operation, and then there will be a 3rd, 4th, and 5th operation coming up as I mill slots and drill a hole in various different locations. The the drilled hole is actually a kind of a tricky operation because the drill needs to, let me get this in the camera here, the drill needs to be drilled on that surface, which means the part needs to be held in a fixture, and then once the clearance hole is milled up here, this is the hole for the electronic connectors, the drill has to make it down through here, down to here. And in the past, I just used a jobber length drill bit with a lot of stick out and just kind of hoped it would find its own center. And then I went on a kind of a quest for, does anybody sell a spotting drill, a long spotting drill? And well, I finally found one. There actually was a company that had a long spotting drill. So I'm going to try that operation with the long spotting drill and see if it improves my accuracy, because the hole that I'm drilling is the hole for the axle for the lever, and the relation between the lever and the surface of the mounting surface where the circuit board mounts, that relation is one of the more complex and difficult, and I mean requires a lot of precision to get it right. And in the past I've never been able to just hit it right the first time, so I always end up hand fitting my levers, and it'd be really nice to either not hand fit the levers or maybe minimize the amount of hand fitting. So I'm going to run the batch, turn the cameras off, and come back for the third, fourth, and fifth operations. First and second operations are complete and the parts are looking really nice. So now I need to do the third, fourth, and fifth operation. The third operation is not really that challenging. Let me grab a part here. I've already done one, so this is just cutting a slot in the bottom of the controller housing. The long slot is to provide access for the connectors on the circuit board, and the little notch out here is to provide access for the drill and tap to go down this way and drill the hole in the surface. So I'm using, once again, using the Bobcat array function, and I've already got the tool path tested. This one isn't very exciting, but hey, you gotta do them all, so let me got the option stop turned on. So, ramping in, going fairly slow. It's a 1/4 inch 3-flute cutter end mill running at 10,000 RPM. And yeah, I could probably go a lot faster, but having put this much time into the part, I'm kind of just taking it easy, taking it slow, because there's not much material there. The remaining material left after the slot is completed really isn't that much. And now we're moving over to the second part. So I'm cutting at 10,000 RPM, 30 inches per minute, ramping in, and it produces an excellent result. And yeah, I know I could probably go a whole lot faster, but this does produce a good result. So I'm going to go ahead and run all the second operation parts. The third operation is also fairly uninteresting, but it does use an 1/8 inch end mill. which is always a slightly nervous thing. The little guys I'm not totally comfortable with them yet. And then the final operation, the fifth operation, is going to be drilling the hole at an angle using a special drilling fixture and a new tool that I just got. This one was somewhat difficult to find. This is an 1/8 inch diameter, 6-inch long spotting drill. And in the past, I'm drilling for a 1024 thread, and in the past I just used a 1024 tap drill jobber length and was always a little bit nervous about, well, is that thing walking around a little on the end there? And the relation of this hole to the circuit board mounting surface is pretty critical, because this is where the hand control lever, which has a little bump on it, and you press the lever and it's got a hinge on an axle, and it presses against a little tactile switch on the circuit board. And so locating this hole, it really, the closer the better. And so it's going to be interesting to see if my accuracy is improved any using this long spotting drill. And boy, that was a hard one to find. I guess it's a really specialized thing. Most 1/8 inch spotting drills are 2-inch overall length, and it was somewhat tricky finding a long one, but I found one, and we're going to see how it works. So, see you later. All the third operation parts have been done successfully. Now it's time to drill a hole and cut a little slot. And just in case anybody is interested how this all fits together, here's the controller housing. Here's the little circuit board, a custom-made circuit board for the NQALHA. And just in case anybody is wondering, this is the kind of work I used to do when I was working. I mostly did software and electronic design with a little bit of mechanical design, and now I'm just doing machining and making NQALHAs and working with glass. So on the end of the little circuit board is the USB connector and a switch, and they have to kind of go into the, get this guy here. So now we've got the switch and the USB connector, as well as the connections for the rest of the electrical, and everything fits perfectly. So I'm going to be running the array here. Let me select that and just do a quick sanity check. Yep, looks reasonable. So here we go, a hole and a slot. Boy, that was exciting, wasn't it? The hole, and nothing but the hole, so help me hole. Here we go with an 1/8 inch milling cutter, 10,000 RPM. Being very, very careful at 20 inches per minute. And probably heard a little bit of chatter. It's a thin section and unsupported, and oh well. Sounds funny, but parts come out really good. So I'm going to run this batch, get all these guys done, and then the last operation on this part will be the long spotting drill and the hole at an odd angle for the 1024 thread. And no, I'm not going to try power tapping it, because the tap doesn't have enough stick out. I have to hand tap that one. Either that, or maybe one of these days I'll order a long 1024 tap so I can do it all in the machine, but I don't have one today, so just tap them by hand. And the way the little slot is oriented to allow clearance for the tap, it's kind of like a built-in tap guide to keep the tap straight. So yeah, maybe someday I'll get a long tap. The fourth operation has been completed successfully, and now I'm on to the last operation, which is drilling the hole at an angle through a slot and trying to get the hole as precise as I possibly can get it. As I said a little earlier, I'm going to be trying for the first time the long spotting drill to see if maybe that can improve my, my precision a little bit. I'm using a special fixture. Here's the fixture here, and I only made one of them, so I kind of always have the question, well, should I make another fixture or just suffer the slow operation of dealing with the one fixture I have? And for a lot of the other parts, I made some new fixtures, some new tooling plates. But for this one, you know, the process goes so fast, it's just a couple of holes. The cycle time is so low, and I think I'm just going to leave it with one. So getting this guy set up, it's always a bit of a nervous operation, especially with the rapid speeds on the mini mill. So I'm going to go through a little bit of a setup procedure here, just to kind of double check and triple check in order to get that the 1024 tap drill down through that clearance slot down to where it needs to drill, and then to drill the depth it needs to drill. I have to have a pretty good amount of stick out, but I like to minimize the stick out to try to keep the drill as under control as I can, so I get that stick out as close as I can get without running the collet holder into the part. And so I'm going to be checking some stuff here, kind of like hand checking and double checking and cross checking, and then I'll try running a real part and see if I actually have a good time doing it. So the probe, as you can see, the probe is mounted in the machine because I set the reference Y surface to the surface of the fixture here, and then the X and Z zero are the same as they always are for work offset 2, which is Z zero on the bottom of, well, on the bottom surface on the vise surface, and X zero up against the little stop over here. So I'm gonna load up the program and go through my standard setup here with reduced rapid, option stop, and that's tool 30, single block. And I'm gonna stop the spindle here and just do my first sanity check, which is to put the part in the fixture and observe that, yes, in fact, it does clear. Now just let me grab another drill bit here, and actually I don't really have a drill bit available, so take a piece of stock. This is what I'm trying to do. Here's the slot, and the drill bit needs to go through the slot into the part like that. And the slot, since the only purpose the slot serves is clearance for the drilling operation, and then when I'm assembling it, I get the Allen wrench in there. I don't want this thing to be too gigantic, so I try to make it as reasonably tight as I can. And so always like to just verify that, yeah, that looks reasonable. It looks entirely reasonable. So I'm going to look at the G code here and see that the depth here is 1.754. So I'm going to go into jog. Okay, 1.754, and going to, what? My wife getting the car out of the garage. I always like to be aware of strange noises in the shop. So that looks by the eyeball to be a reasonable, sane distance. So I've now done my cross-check, and I'm going to load up a part and hope it works. After all this work on these parts, it would really suck to screw one up at this point. So here goes. And that looked completely correct. And here comes tool 45, and here we go. So we have, I don't know if you can actually see it here, but we have a successful hole. Looks like it's in the right place. Had no clearance problems, no stick out problems, no pain, no failure. Looks like we're sucking the cess. So I'm going to finish running these parts, and when I finish this batch, this will conclude the aluminum machining. And after that, I have some steel parts that I'm going to machine, mostly on the mini mill, but I think I do have some parts that I need to make on the manual lathe. I'm not sure that I'm going to show the video of the steel parts, because here they are. They're laser cut steel parts, and all I'm going to be doing is drilling some holes in them, and hey, that's not that interesting. So there's a good chance that this is going to conclude the series. In the previous series of NQALHA Production Run 4, I showed some more of the NQALHA stuff, the final assembly and things like that, and really nothing is going to change on this run once the parts are done. So I think this may very well conclude the series, and thank you for watching. It's been fun.